Okay, we start up again. Going to continue with a little bit more numerical theory. Any questions before we begin? Okay. Then let us have a look at a problem, very, very famous problem. We have something, an advection equation. Better do it properly here. One-dimensional advection equation. Sort of the two first term in a Navier-Stokes. So you have a time derivative of something, we can call it a velocity, and then you have a nonlinear term in a Navier-Stokes. If it were velocity, you will here write u times du dx. Here we cheat, so I have something constant, du dx equals 0. And now I say a0, he's a constant, and he is bigger than 0. So, of course, in the real equation system, the Navier-Stokes, yeah, it should be a velocity, hence nonlinear term. So it's a linear version. We have linearized. We have to do this to be able to do an analysis of this one. Now, make a discrete version of this one. And typically, the first you try, that's a forward time scheme. Forward time, first order Euler scheme. And then you use central space. That is quite standard, actually. So you replace this time derivative with u at a given point, index I in the x direction. Time level, I use n for time level. So here you now have the difference at the same location divided by delta t. That's a first order time derivative for you. And then you have a 0. And then we need a space derivative. So if this is my x, this is my point I. Yes, I'm going to use the neighbors. When you use a central scheme, it should be symmetric around the center point. So I create a first order derivative by taking I plus 1 and I minus 1. So ui plus 1, time level n, minus ui minus 1, time level n, divided by 2 delta x, divided by the distance between them. That's a second order numerical scheme. So this one, it's 0 plus order delta t delta x square. First order in time, second order in space. We'll see later how you find these orders. And this one, as you see, is very, very easy, very simple. It's an explicit scheme. You have one unknown if you know what happened at time level n. Very easy to march the solution forward in time here. No problem at all. So this was sort of the first attempt they tried. And this one doesn't work. He explodes. He's unconditionally unstable. No matter what you do, he's going to explode. I'll show you. So what then did they do? Well, they cheated. Well, maybe not cheated. They just used a different scheme. Still forward time, but now you use a upwind scheme. Upwind scheme. Say, I should remove this one down here somewhere. Let's see now. I plus 1, I minus 1. A lot of people, they prefer to use indexes here instead of these points P and west and east and so on. means the same, but I mean when you do the programming here, you're going to use these indexes anyway, so I think that one is much more easy. So if this is space, and then you have time here, this is time level n, this is time level n plus 1. Okay, so for this recipe you are using the center point and you are using these 2 points to create or to find this new one up here, right? For the upwind scheme, then we do a little bit differently. The time will be exactly the same, but for the space derivative, now we say that this information, the space derivative here, he is traveling with a transport velocity given by this A0 thing, and he's positive. He goes in this direction, A0 positive. So now I'm going to create a derivative by using the values upstream. So I don't use this one anymore. I'm going to create a derivative just using these 2 points. So now it's not symmetric anymore. And if we then do as follows, A0 and then ui n minus ui minus 1 n divided by one single delta x. That's the trick. That means if you look at it as a central scheme, you have actually created a derivative somewhere between these 2 points, somewhere here. But this is the location for our unknown when we solve this one for the new velocity. Hence, this is going to be a little bit different when it comes to the orders. So this one equals 0 plus order delta t and then only one single delta x. So let's try these 2 and see what happens. Any questions to that one? Should be familiar. Okay. So let's have a look. So here we have a problem in the x direction. We have a signal, an unknown equals 0, except in a range, and then all of a sudden he is 1. So fairly impossible problem, but it's purely academic anyway, it doesn't matter, that's for demonstration. So this is the initial state. You have a signal and he has a jump. Now what will this equation actually mean, an advection equation, with a constant transport equation? He should actually then just move this signal with a constant velocity to the right. So we have the exact solution. That's the red square here. Of course, we don't hit him precisely because I have a limited number of cells. But let's now choose the central scheme. And I had chosen now my velocity and my scaling so that my Courant number is 0.1. What was the Courant number? Well, that was the length, the velocity times delta t. The length you can go during one time step divided by your cell size, delta x. And no, you are not allowed to travel longer than 1 delta x during one time step for explicit methods. So this one should be stable when you think of Courant numbers. So if we run this one, you see what happens. He is totally off. Really, really bad, unstable. So any change in the signal is going to be enhanced, creating a lot of oscillations And I mean, we can slow down the process if you like. Try with even smaller delta t, meaning you have even smaller time steps. Let's see. You get exactly the same. It just takes a longer time. So that was the central scheme, FTCS. And the conclusion then in the old days, it doesn't work. Throw it out the window. You can't use it. That's not the entire truth, but never mind. Okay, so the remedy then, first order upstream. First order upwind or upstream. So there you see the effect. Yes, it's stable. It's stable. I have a Courant number of 0.1, no problem there. But you see the price you pay. You smear out these sharp gradients. And what's happening here? We are actually introducing viscosity into the problem. But we don't have viscosity. It should be 0. So it's far from the correct solution. And then people have tried a whole bunch of different things. I can show you here. You have what's called a Lax-Vendroff problem. A scheme doesn't help. You have a hybrid scheme. You can take, say, 50% of each of this upwind and this central scheme is stable, but still you get something smeared out, and also you have undershoots, overshoots. That's also impossible. You shouldn't get a new solution outside the range of your initial values. So it really doesn't matter what you do here. You can even try with, I think I had, we have some quick, we can skip that one, but fully implicit. Fully implicit schemes, they are normally unconditionally stable. Well, actually he is stable, sort of, but the solution is not nice. So implicit schemes can be very, very dangerous indeed. And then we have more advanced schemes, which I then wanted to address. A linear upwind. Still, you get something weird. It's stable actually, but it's not bounded. It's definitely have some over and undershoots. So no, we don't really like any of this. So what do we do? What do we do? First, I want to identify the price we pay for using an upwind scheme. Not only first order, but even second order. Well, first of all, the problem at hand, advection equation. How interesting is that one? Of course, in the end, we are going to have a viscosity and a double derivative at this site. Of course, we are going to have the Navier-Stokes in the end. So this will actually make it possible to have a stable scheme anyway, even with a central scheme. But we have to be careful. More about that later. But for now, why do we achieve the, say, viscosity where we don't have viscosity when we choose this scheme? This one explodes. Okay, for now, throw it out the window. This one. Have a look at that one. How do you investigate such a scheme? The numerical analysis of it. That is where we are using finite differences like this, not finite volume, and we insert Taylor series. We're going to need a Taylor series for all the, say, the offset of a center point. And which should we choose as a center point? Well, it's quite natural to choose this one. Time level n, center position I. So we will keep this one. This one, there we have to insert a Taylor series in time. And let's see, we are on this upwind scheme. This one is a center point already. And this guy, here we need the negative Taylor series. Okay? Then we insert that one. Let's see what happens. Let's see, for the time derivative, we have the same term for both schemes. I'm looking at this one now. So inserting Taylor series, you should then get something like this. A positive Taylor series in time. What will he look like? Well, he should then be ui, time level n, and then plus delta t, and then you'll have u time derivative. I use a dot as time derivative. And then you will have the next term, delta t squared half, u double derivative plus, and then even higher order terms. Minus the center point, minus uin, something like that. And then you see the center point, he will drop out, and we are left with these two. That's fair enough. What about on the other side? Plus. And then we had a0 divided by one single delta x. And here I want the center point minus the negative Taylor series. Okay, center point minus the negative Taylor series. What's that? Well, you start then with u, I, n. We can do it like that. And then we go in the negative direction, hence we're going to have a minus delta x. And now we have u space derivative. Just use an ampersand for that one. And then we'll have plus delta x squared half u double derivative minus, and then even higher order terms. There we have it. Now let's see, we need some more space here. Any questions to that one? Yeah.
I was wondering, what's the difference between the upwind scheme and the backward difference? Isn't it exactly the same?
No, when you're talking about a backward, yeah, I should mention that actually. These two schemes I've shown you here, they are explicit. Both of them very easy to solve. You have one unknown and just throw everything else on the other side. You can update the unknown directly. If you want an implicit scheme, backward time, then you have the following problem. And then you see you have three unknowns. You have to solve an equation system to fix this one. So an implicit scheme, that is harder to solve. Then you will call it a backward time. Okay? Other questions? Okay, we continue. Let's see now. We have this one then actually equal to 0. Now, this one should actually be exact, should be correct. I mean, if you just take enough terms in the Taylor series, this one should be as precise as you want. So no problem there. Okay, let's see now. The center point here, he falls. And the center point here, well, he will also fall. No problem there. Okay. Then what are we left with? Let's see now. I will have one term here. but divided by delta t. So we'll have u time derivative. So that's that one. Should we keep it? Yeah, why not? We can keep it like that. Then the next one, well, here's positive. And I divide by 1 delta t, so we'll have something delta t half. And then a double derivative. Something like that. And then even higher order terms. Okay. What about in space? Here we will have minus minus becomes positive. So this term will survive. And we divide by delta x. So I will have plus a0 multiplied with u space derivative. And then I'll have minus and minus. Let's see now. Divide by 1 delta x half, u double derivative, something like that, equals, and then not 0 but higher order terms, something like that. For this equation, I just inserted the Taylor series and reorganized it a little bit. Some people call this one the modified equation. That is not the entire truth, at least in not my eyes. So it's the start. But here you can tell a lot. First, you can say your scheme is consistent. Meaning, if you take lim here of this equation and let all your deltas, delta x, delta t goes to 0, what are you left with? This one disappears, this one disappears. You get the original partial differential equation back. Consistent. You're solving the correct equation. Of course, this is essential. Most schemes are going to be consistent anyway, but it should be actually investigated. It would be very embarrassing if you solve the wrong equation. So, consistency, yes, that's important. Consistent. Good. Also, you see the order. The truncation error, how big is that one? The biggest error we have is of order delta t and is of order delta x. Yes. So we have actually our scheme, f forward time, and then it was upwind scheme, equals order delta t, delta x. So we have the correct order, or you can find the order from this, say, call it modified equation if you like, but okay, so far so good. No questions to this one? So when it is consistent and you have enough, say, information, boundary conditions to have a well-posed problem, as we call it, then the only requirement for a solution is then stability. Okay, never mind. Let's see now, we don't need this one anymore. So let's get rid of this. Now I want to find what I call the modified equation. Get rid of any time derivative that's not supposed to be there. This one. This one is okay, we want him. He's a nice one. But I want to remove this double derivative in time. Replace him with something else, namely space derivative. How to do that? Well, if this is equation number star, then I take the same equation, I multiply him with minus delta t half, and then I take the time derivative of the entire equation. That's allowed. What do we get? Then you see the first term here, here's now going to be a double derivative with respect to time, and then multiply with minus delta t half. So I will have minus delta t half u double derivative. That's him. Beautiful. What about this one then? Well, he will be triple derivative, and also he will have delta t square, so he's very small anyway. Forget him. What about that one? That's not so funny, is it? What do we get here? We multiply with minus delta t half, so it should be minus delta t a0 by 2. And then you have a mixed derivative, time and space. Something like that. What about this one? Well, he's also going to be a higher order. You have delta t multiplied with delta x. He's not important anymore, so forget about him. But now I have, if I add these two equations together, I get rid of this double derivative with respect to time. But in the process, I produced another time derivative, which I don't want either. Get rid of him. How to do that? Well, we have something negative here. So if I now invent an operator, delta t multiplied with a0 over 2, and then I take the space derivative of the entire equation, d dx of star. What do we get? And you see the first term here, time derivative, and now space derivative is going to produce exactly what I need to get rid of this guy. Delta t a0 half, and then you cross derivative. So this one will now be removed when I add these two together. But we are not done yet. What? We have something more here. Well, this term will going to be some delta t square, and then third order derivative mixed. No, forget about that one. But this one, he's going to be what? Well, he's then going to be plus, what will it be? Delta t a0 squared half, and then I have u double derivative. Something like that. And this one also even higher order terms. Now add everything together. What do you get? I get rid of this term. They fall. These two terms, they will also fall. So what am I left with? Let's see now. I'm left with something like this. I have the time derivative, and then I have this term plus a0 u space derivative, and that's my original equation, so that's beautiful. Let's throw everything else on the other side. Equal. This one then becomes positive. So here we have delta x half u double derivative, but I have a u double derivative here as well. And this one becomes then negative, minus delta t a0 squared half multiplied with u double derivative, and then even higher order terms. This is the modified equation. And here you can actually learn a lot. First of all, we have obtained a viscosity. In my original equation, this one was equal to 0, but now he's not 0 anymore. Of course, you can make him as small as you want by choosing small delta x's and small delta t's. So he should be possible to handle. If I had chosen the pure central scheme, the one that was completely unstable, you could do the same there. Then this term will not be present. You will only have a negative term here in front of the double derivative. What will that mean? You have negative viscosity. This then will act as a negative numerical viscosity. Negative viscosities, thank you very much. When you have a signal and you have positive viscosity, you will smear out the signal. He softens down. That's the effect of viscosity. If you have negative viscosity, he does the exact opposite. Of course, he's going to explode. unconditionally unstable if you're using only the central scheme. This is not present then. But now with the upwind scheme, yeah, we can make this actually stable. But then the demand will be this one better be positive. It must not go negative. And there you see we'll have a limitation on our time step. And what will it be? Well, let's rewrite this one a little bit, can't we? If we say 1/2 on the outside, that should be okay. And then we'll have, I have something is missing here, isn't it? I have one A0 too much. Delta x minus delta t A0 square, u double derivative. I'm missing one A0. Because what we should get here was actually the Courant-Friedrich-Levy condition, so it should only be one single A0 here. Never mind. You can look it up yourself. Anyhow, as a stability criteria, I want positive diffusion, positive numerical diffusion, we have to call it. Diffusion will then imply the Courant number, which then is delta t times this transport velocity over delta x has to be smaller than 1. So you get actually the stability criteria from this modified equation as well, if you do it right. Any questions to that one? So my point is, yes, you can make it stable using first order upwind. But what you do is actually to introduce a viscosity. And you introduce it with this term here. Where was it? Delta t. Yeah. I think I forgot to multiply that one with A0. Never mind. The effect here is actually quite bad. Now imagine you had a problem using viscosity as well. Then you have an additional term in this equation. Then you will have it something like this. Then you'll have the kinematic viscosity and then double derivative. He will then be part of the original equation. So there you can see choosing an upwind scheme. Yeah, you can make this term so big that the total sum here is positive, or 0 if you can make it. Then it's stable. So it stabilizes a lot. But what you actually do is you are increasing the viscosity. That means in practice you think you are simulating using water, but you have doubled or tripled or quadrupled the viscosity, so you are actually simulating a totally different liquid or a totally different fluid. So it comes with a terrible price, especially when we look at the first order upwind scheme. We have more advanced upwind schemes nowadays, which then is second order and even third order accurate. So they are not so terrible. But still, all of them will introduce, say, some numerical viscosity, which we don't like. This negative thing here, he's not so funny. If you can keep this term smaller than the kinematic viscosity, then it should still be stable, meaning if you had chosen the central scheme, then this one is not here. Then you only have these two. Okay, then you can find a stability criteria here actually. You have to choose delta t so small that the total viscosity has to be, say, positive. Of course, this analysis was based on a linear equation, and in the real life we don't have this A0 thing. We have the velocity, the unknown, multiplied with the derivative of the unknown, but then we couldn't do the analysis. So you have to take this one with a little bit grain of salt for the real equation system, the nonlinear equation system, but the effect is here. Upwind schemes introduce viscosity. Be aware of that one. So know what you are doing. Okay, I'm going to continue then tomorrow looking at the advection and diffusion together, and then see the more modern numerical schemes that is available for you in OpenFOAM. So then I think it fits to stop here. Any questions for this? That's okay? Okay, then we stop here.